Hello, welcome to Rehandran. I hope you're doing well. So in this video, I'm gonna talk about voltage. Voltage, which is the scalar quantity of electric field. So it is very important, and in circuit analysis, we use voltage, not electric field. So it is a very one of the most important parameters um, in all of electrical engineering. So in an electric field, say this is an electric field in 3D space. So there's no doubt about it that this is an electric field. It is diverging, and this is an electrostatic field. So it is diverging from its source. So by convention, the positive source has diverging flux. So sorry. So positive source has diverging flux, and by convention negative source has convergent flux, and negative sources are called sinks. So that's the basic idea of field and flux. And in an electric field, a, a charge or a charge carrier experiences coulombic force, which is say that coulombic force is, so say this is point A and this is point B. So if I take a point charge here q1, say charge 1, and this is the charge, this is positive charge, say positive charge, and this is q. So this is q, this is q1. So q1 is at B, and I'm not taking it from it B to A or something. It's just stationary at B. So what will happen is that, because B, the position B in 3D space, mind you, this is in 3D space. This is because I am not using any computer simulation. I'm just using a 2D board, so I cannot uh, show you the third coordinate, the third axis. So the third axis is like this, perpendicular to the plane of this board. So in 3D space, the B position, say r xyz, so this position is inside the electric field, the electrostatic field. So this charge will face a force. This charge will experience a force, so that force is coulombic force. So say if coulombic force is q1 q 1 by 4 pi epsilon o. Say this interaction is in vacuum, not in material or medium, not in any medium. So, and the distance between the two is squared. So this is the coulombic force, electrostatic force experienced by the charge q1. Force on charge q1 due to electric field produced by charge q at O. The force is, by specifically the force is OB. Force is OB, which is 1 by 4 pi epsilon O q1 cross q by r uh, B minus R O, the position. So R O, which is Q, and R B minus R O. in the numerator. So this can be also stated inversely. So this is equal to minus fbo. So this is the Coulomb force experienced by charges. So q1 experiences fov force, and q also experiences charge force bo. Okay, so it's both true for the two charges. Say this is the charge at B position. Charge is at B position. Electromagnetic fields are force fields, okay? So they exert force and momentum. They store energy and transfer energy. So field strength of the electrostatic field is, it is denoted by E, the field intensity, or field strength to be more specific. This is the electrostatic force itself per charge. So charge q or small q, which one you prefer. Now if I say what's the exact um, expression of field strength, the expression of field strength is 1 by 4 pi epsilon o. So I'm considering this interaction, this field in vacuum, not in any medium. So if I consider this field in electrostatic field in medium, there will be the permittivity will change. This is the permittivity is the parameter by which we determine the field and medium interaction or material interaction. So this is the by r square, and electric field strength at a point, say B, that in that point. So for that point, if I take the r origin as ro as origin, so if I take ro as origin, so q r b minus r, or if I flip this, it will be like r minus rb, rb minus r. So this is the magnitude, say q. So or if I wanna say be more standard, so this r, if I just flip it, so 1 by 4 pi epsilon o q r minus rb by r minus rb cube. So this is a more standard form. So this is the field strength of the electrostatic field, strength of the field. So now what I'm gonna do is I'm gonna discuss about the, this is a vector. So I'm gonna describe this electrostatic field E, the field strength, in terms of its scalar parameter, which is called potential or voltage. So in theory, uh, electrostatic field extends to infinity. Say this is infinity, and beyond this, the electrostatic field doesn't exist. So this is infinity. Say, so this is say v. So this is r1. Say this is, or say ra, rb, and this is infinity. So there, here voltage is zero. So this is zero potential, and at ro, or the origin, this is voltage maximum. And as we move further from the source, the voltage decreases. So VA is greater than VB and so on. So now consider this. I wanna uh, take a charge, a point charge Q, say this is Q1, which is a positive charge, which is at infinity, and take it to point B. Okay, so if I want to take it from infinity to point B, what will happen? It will be like I would have to do work externally, because when I take this inside the electric field, I would have to exert external force. Hence, as I am exerting force, I am moving the charge Q, so I am doing work, which is work obviously. So moving a charge from infinity to a point inside an electric field is doing work, and work per charge is the voltage. So if I have to say, by definition of work, say differential work. So differential work in electric field is minus f differential length L. You can say L, or you can just write dr. So this is very important, and this is just equal to, this is just analogous to the mechanical work done. This is basically the same. So for full work, I have to integrate over the path. So minus means that I am exerting force from external and moving the plus from lower to higher potential. So there is a minus sign, because the electric field is directing towards this, and I am moving the charge opposite. I'm moving the charge opposite to the direction of electric field, so there is a minus sign. So integration f dr. Now what I'm gonna do is, this is Coulombic force. So force is QE, F equals to QE. So equals Coulombic force by charge. So minus Q, or smaller q, which one you prefer, this, then this. I like this. And now the full work from infinity to B. So this is minus q. So from infinity to say minus infinity to B dr. So this is very important, and so this is basically the work. And if I have to define voltage is, or potential is, work per charge. So V, which is We by Q, which directly gives me minus infinity. So now I'm not gonna use B, I'm gonna use a more standard universal form r distance, which is r distance away from the main source charge Q. So E dr. So this is the expression for voltage. So if I write this a little bit clearly, so voltage is defined by the work done in taking a charge from infinity to a position finite distance away from the source in an electrostatic field. So this is voltage. Now if I wanna uh, de- if I wanna describe this voltage a little more indefinitely, so indefinite integral, I will use indefinite integral. So this is a more general form. So, and if I just take like this, so if I take the indefinite integral to the left hand side, it will look like this, d by dr, which is a very important conclusion. If I want to break this d by dr, it will be basically this. So in 3D, mind you, we are dealing with electric field in 3D space and in vacuum. So the r is spherical coordinate system r, so it will obviously have components xyz. So this is the full partial differential partial differential relationship, which tells us that, so this is obviously the Nabla operator or vector differential operator. So this tells us that electric field intensity or the electric field strength is the gradient of the voltage. So it is very important, and it is very fruitful for us to understand this. Now I'm gonna just briefly describe the voltage difference. So this is the main, expression for voltage in terms of electric field strength and vice versa. And if I wanna take, I wanna express electric field in terms of voltage, so this is the Nabla operator voltage, so gradient of voltage. Or, so now I wanna discuss about voltage difference. So what is voltage difference? Say the charge q1 is already inside the field and it is in b, position b. So I want to take the charge q1 from b to a. So what will the work? So that will be the work. And what my question is, what is the value of that work? The value of that work is the difference between voltage b and voltage a. So this is very easy. So voltage, so I'm taking from b to a, no doubt about it, edr, which will obviously give me v a minus v b, to be exact, or vb minus v minus vb minus va, sorry, minus, so vb minus va. So this is the voltage difference. So this is very easy. So we have got voltage in terms of electric field, and electric field in terms of voltage. Electric field is the gradient of scalar parameter voltage, and voltage difference is when in approximity of electric field, when I try to move a charge or charge carrier from one point to another, it it gives us a voltage difference from that point to the another, and work is done. So this is very important, and I hope you understood it. So this video is ending here. So I hope you have understood my explanation, and if you have any problem in understanding and if you have any suggestion for me, you can tell me in the comment section. Thank you.